Are we live? Guys, hello. Yes, we are live. Hello, everyone. Welcome to the second day of the journey. Today is we start with the third. I mean, not third. Yes, fourth step of the tutorial, and this step is called Hello Triangle. I'm guessing that we're going to render some triangles here. Or yes, let's check it before. That talks about fragment shaders, vertex shaders. This is going to be a long tutorial step, I guess, because like there is a lot of information in this chapter. Yes, before starting, I just want to get my Twitch chat out. Sorry. Pop out chat, close. Where is the pop out chat? Here. Yes. Okay. You guys can see it. You guys can see the code. You guys can see the tutorial. I could start, I guess. Yes. I changed out my tasks window, as you see. And I also found my water bottle. Yes. Okay. What does it say? In open... Oh, first of all, I think we have to fix the hold button bug, no? From yesterday. We couldn't address that issue. But I feel like if we address that issue now, we won't get further. So I think I'm going to address that issue right after I render my first triangle on this tutorial. I mean, like after this step of the tutorial, I will just address that issue with the holding F key. Okay. In OpenGL, everything is in 3D space. Okay. But the screen or window is a 2D array of pixels. So a large part of OpenGL's work is about transforming all 3D coordinates to 2D pixels that fit on your screen. So you get a 3D object space, 3D space, but your display is 2D, so you have to transform these all 3D coordinates into 2D pixels. So, and you can store the 2D pixels in two arrays. I mean, you can store it in one array also too, but yes. And you just have to transform these 3D pixels to the array elements. And that is managed by the graphics pipeline of OpenGL. Is there any more? No, there is no description. The graphics pipeline can be divided into two large parts. The first transforms your 3D coordinates into 2D coordinates, and the second part transforms the 2D coordinates into actual colored pixels. So, okay, this is pretty straightforward. In this chapter, we'll briefly discuss the graphics pipeline and how we can use it to our advantage to create fancy pixels. So we're going to create pixels. The graphics pipeline takes as input a set of 3D coordinates and transforms these to colored 2D pixels on your screen. Okay. Okay, the steps get yield outputs that which then be taken from the next step as the input. All of these steps are highly spatialized. They have one specific function. Each step does one thing and one thing only. Therefore, it can be executed in parallel because does only one thing. Because of their parallel nature, graphics cards of today have thousands of small processing cores to quickly process your data within the graphics pipeline. The processing cores run small programs on the GPU for each step of the pipeline. These small programs are called shaders. Okay. Some of these shaders are configurable by the developer, which allows us to write our own shaders to replace the existing default shaders. This gives us much more fine-grained control over specific parts of the pipeline, and because they run on the GPU, they can also save us valuable CPU time. Shaders are written in the OpenGL shading language called GLSL, and we'll delve more into that in the next chapter. What is our next? Okay. I mean, directly under this step. Below you'll find an abstract representation of all the stages of the graphics pipeline. I already know this because of the computer graphics lecture on my university. In my university, you basically have 6 steps here. Vertex shader is where you put the 3D models. I mean, like where you put the vertices the 2D array, and after that, this geometry shader should be optional because I only saw that the vertex shader and fragment shaders are implemented. The geometry shader, I suppose, connects these dots and complements with another dots, and shape assembly then probably draws the edges. And after that, after that we are testing, I guess, if a specific triangle is at front or in the back, and after that we are painting the 2D pixels with the colors of the triangles, which is on the back, which is on the front, I don't know. And after that we rasterize everything. No, I'm sorry. Rasterization comes first, and then it is colored with our code, and then we're just testing if which triangle stands on front and which stands on the back side of the display. As input to the graphics pipeline, we pass in a list of 3D coordinates that should form a triangle in an array here called vertex data. Okay. This vertex data is a collection of vertices, as you can understand from the name. A vertex is a collection of data per 3D coordinate. So these are 3D coordinates. But for simplicity's sake, let's assume that each vertex consists of just a 3D position and some color value. So each vertex consists of an RGB color and a 3D position, which is also a 3 vector with 3 inputs. In order for OpenGL to know what to make of your collection of coordinates and color values, OpenGL requires you to hint what kind of render types you want to form with the data. Do you want the data rendered as a collection of points, a collection of triangles, or perhaps just one long line? How does it... Okay, never mind. Those things are called primitives and are okay. If you for example, if you give GL points to the vertex shader as your form, it just displays these 3, I guess. And if you, for example, give GL triangles, then it should connect these dots here, I guess. The first part of the pipeline is the vertex shader that takes as an input a single vertex. The main purpose of the vertex shader is to transform 3D coordinates into different 3D coordinates. What does that mean? Okay, I don't know. I zoned out. The main purpose of the vertex shader is to transform 3D coordinates into different 3D. Okay. And the vertex shader allows us to do some basic processing on the vertex. Probably, we're going to, not probably, it's I mean, that's highly likely that we're going to transform the object space into world space, or later on that. The output of the vertex shader is optionally is the key here, passed to the geometry shader. The geometry shader takes as input a collection of vertices that form a primitive and has the ability to generate other shapes by emitting new vertices to form new or other primitives. In this example case, it generates a second triangle out of the given shape. True. The primitive assembly, that is like just a filler. And the output is like the shape, the triangle we want to render is given it passed onto the rasterization stage. At this stage, the triangles are mapped to pixels. Like you can see here, these are pixels. These are pixels, and yeah, as you can see, this shape, the triangle, occupies these pixels on the screen. Resulting in fragments for the fragment. This is called a fragment, I guess, this single pixel. And like before the fragment shaders run, clipping is for one. Clipping is like the thing where that happens if, I mean, if your display if your display can display if your monitor can display the, I mean, some vertices of this triangle, it is clipped out. I read all this. Calculate final color of a pixel, and this is usually like this fragment shader calculates the color which can come from a light source. I don't know, it can happen through a shadow, color of the light. After all the corresponding color values have been determined, the final object will then pass through one more stage that we can call the alpha test. This is because this is probably the alpha test is like the alpha value of the RGBA colors, and it determines whether some objects are transparent or not, I suppose. And this stage checks the corresponding depth. Also, the set buffer test is executed here, I guess. The set buffer test accomplishes this thing where the color of the triangle on the back is simply not rendered. The stage also checks for alpha values, okay, and blends the objects, okay. So even if a pixel output color is calculated in the fragment shader, the final pixel color could still be something entirely different when rendering multiple triangles. This is completely fine, because if your triangle is not on the front and the frontmost, then you're not going to get it. You're not going to see it. As you can see, the graphics pipeline is quite a complex whole and contains many configurable parts. However, for almost all the cases, we only have to work with the vertex and fragment shader. Like I said, the geometry shader is optional and usually left to its default shader. Okay. There's also the tessellation stage and transform feedback loop that we haven't depicted here, but that is something for later. Okay, in modern OpenGL we are required to define at least a vertex and fragment shader of our own. at least a vertex and a fragment shader. There are no default fragment and vertex shaders on the GPU, obviously, because if you want to put your triangles, the GPU won't put the triangles for you, because you want to define your triangles to these render models. For this reason, it is often quite difficult to start learning modern OpenGL, since a great deal of knowledge is required before being able to render your first triangle. Okay, and to get to finally render your triangle at the end of this chapter, you will end up knowing a lot more about. Okay, thanks a lot, I guess. Vertex input. What do we have here? To start drawing something, we have to first give OpenGL some input vertex data. OpenGL is a 3D graphics library, so all coordinates that is specified in OpenGL are 3D, X, Y, and Z coordinates. OpenGL doesn't simply transform all your 3D coordinates to 2D pixels on your screen. OpenGL only processes 3D coordinates when they are in a specific range between -1 and 1 on all 3 axes. Okay, I mean, if it's okay, understandable. All coordinates within this so-called NDC range will end up visible on your screen, and all coordinates outside the screen won't. Okay, understandable. Because we want to render a single triangle, we want to specify a total of 3 vertices, with each vertex having a 3D position. We define them in normalized device coordinates, NDCs. The visible region in a floater. This is simply okay. Okay. I see. So it's like this is like a basic coordinate system ranging from 1 to -1 in both axes. But okay, this is ignoring the z-axis. I mean, yes, any triangle you display between these ranges will be displayed, will be rendered. Okay, we understand what happened here. We can continue with the vertex data defined. We'd like to send it as input to the first process of the graphics pipeline, the vertex shader. This is designed by creating memory on the GPU where we store the vertex data, configure how OpenGL should interpret the memory, and specify how to send the data to the graphics card. The vertex shader then processes as much vertices as we tell it to from its memory. Okay, there are buffer objects, I guess. We manage this memory via so-called vertex buffer objects that can store a large number of vertices in the GPU's memory. Okay. I wonder what number of vertices that is actually. The advantage of using those buffer objects is that we can send large batches of data all at once to the graphics card and keep it there if there's enough memory left, without having to send data one vertex. Sending data to the graphics card from the CPU is relatively slow, so wherever we try to send as much data as possible at once. Once the data is in the graphics card's memory, the vertex shader has almost instant access to the vertices, making it extremely fast. A vertex buffer object is our first occurrence of an OpenGL object, as we've discussed in the OpenGL chapter. I know what that is. I'm going to read through. This is just a basic C++ struct. A C struct. Okay. What's this? A vertex buffer object. It's like an object in OpenGL. This buffer has a unique ID corresponding to that buffer. So we can generate one with a buffer ID using the GL_GenBuffers function. So this function probably, can we read it? Yes. OpenGL's GL_GenBuffers function generates one or multiple buffer objects. Buffer objects are instantiated behind the scenes, and the different IDs are then returned. So we store this buffer IDs in an integer, and then use this buffer and then like store something in this buffer through this ID. Size defines how many buffer objects you would like to generate, and the second argument will then return, and I mean not return, but like write it in. OpenGL has many types of buffer objects, and the buffer type of a vertex buffer object is GL_ArrayBuffer. OpenGL allows us to bind to several buffers at once as long as they have a different buffer type. How do we set the buffer type? Okay. In the first argument, I guess, with the GL bind buffer. From that point on, any buffer calls we make on the GL_ArrayBuffer target will be used to configure the currently bound buffer, which is VBO. Then we can make a call to the GL_buffer data function that copies the previously defined vertex data into the buffer's memory. Okay. GL_buffer data is a function specifically targeted to copy user-defined data into the currently bound buffer. This is the currently bound buffer, VBO. We bind that through this function, and currently bind for GL_ArrayBuffer is then VBO. And copy user-defined data into the currently bound buffer. So size of vertices. Its first argument is the type of the buffer you want to copy data into. The vertex buffer object currently bound to GL_ArrayBuffer target. The second argument specifies the size of the data you want to pass to the buffer. In a simple size of the vertex data suffices. The third parameter is the actual data we want to send. The fourth parameter specifies how you want the graphics card to manage the given data. Three forms: static draw. Data is set only once and used many times. Stream draw. The data is set only once and used by the GPU at most a few times. Dynamic draw. Data is changed a lot and used many times. The position data of the triangle does not change. It's used a lot and stays the same for every render call, so its usage type should best be static draw. If, for instance, one would have a buffer with data that's likely to change frequently, a usage type, of GL dynamic draw ensures the graphics card will place the data in memory that allows for faster writes. So this is probably for like games that have faster movement, I guess, faster camera movement, faster camera angle movement, I don't know. Let's see. As of now, we store the vertex data within memory on the graphics card as managed by a vertex buffer object named VBO. Next, we want to create a vertex and fragment shader that actually processes this data. So let's start building those. Let's create our vertices, by the way. So I don't want to create the same triangle like this here, and I'm therefore going with a loaf with a pizza pizza shape. want to render a pizza shape. What should we do? We should with the shape 8 slices. We should 1, 2, 3, 4, 5. Okay, 8. We should describe our vertices, but our pizza is going to be a little bit rectangular, not so circular. We should define our vertices. Pizza shape 8 slices, vertices for triangle. Maybe there is a tool for that. No, there is no tool for that. Coordinate system online GeoGebra. But can I do this? But I want to create lines to yes, to set my boundaries. I can delete all. Start again. 1, 2. They are at 1, 2. Yes. 1, 2, 1, 2. These are our please don't do that. These are our boundaries. Move around. These are our boundaries. So we want to put in our vertices. So we want 1 here maybe. I don't know, 1 here. 1 here. Oh, this is not a pizza, is it? 1 here. 1 here. And then 1 here. And 1 here. This is way too much triangles for a pizza. Whatever. But what am I doing? 1 here. 1 here. 1 here. 1 here. 1 here. 1 here. 1 here and 1 there. What the yes. So I need the coordinates of these points. How do I get that? Export maybe? View? Oh, nah. I want graphics. I mean, but I need the vertices. Never mind, I'm going to find them myself. Okay. This is too much work, isn't it? Let's try. We're first going to define this vertex. It is should build a float array. Yes. offload vertices. Yes, this first one we are typing in the x-coordinate first, and the x-coordinate is like, does it specify all the z-coordinates are as seen null, so this one minus 0.8 as x, 0.8 f as x, 0.8 f as y, and 0.0 f. Yes. This is a weird convention because like it doesn't group them in vectors. We're just going to type 3 floats, and okay, the OpenGL will do it. So this one is the second one. What's the coordinates? Minus 1.0 f, and the third one is x is null, 1.0 f, null 0.0 f. Third one, fourth one, and x is the same with this actually. But the first is not a negative but a positive, and this is also the same. And after that we have we have 1.0 f, null 0.4 f, and 0.0 f. After that we have basically the same, but this one. After that we have, okay, we have this one but negative. After that we have probably this one but negative x, negative y, I mean, sorry, negative y. After that, oops, we have this but negative y. After that we have this one but negative y. After that we have this one but negative y. No. What am I doing? Is it this one? Yes, sorry, this one. After that we have this one. Wait. We put in this one, we put in this one. Should be this one. Yes, it's this one, but minus in y component. Where is the, yes, we should have put We should have put this one too. It's -1 0.4 and 0.0, of course. And this is the same, but -0.4, and at last we have -1.0 f null 0.0 f 0.0 f. I hope I and the middle one, of course, the middle one is also a vertex. Null point null, null point null, null point null. Yes, this should be it. These should be the vertices. Vertex shaders. Vertex shader, I think, is another file that we have to write. People like us.
Tufted psychopath, the king dropped his crown.
Modern OpenGL requires that we at least set up a vertex and fragment shader if you want to do hello, by the way, do some rendering. So we will briefly introduce shaders and configure two very simple shaders for drawing our first triangle. In the next chapter we will discuss shaders in more detail. Okay, let's see. The first thing we need to do is write the vertex shader in the shader language GLSL, and then compile this shader so we can use it in our application. Below you'll find the source code of a very basic. Can I get some Git repository? Because I mean, do we need to write it in another file? I guess so, no? Let's just add a new source file. Where is it? Where is it? Oh, here it is. I'm blind. What am I typing? This is HLSL, but we need GLSL. Is there any extensions? I guess not. Weird. I think I'm just going to go and browse for extensions here. Manage extensions. What can I find? What can I search? GLSL maybe. 2 volts. This is too not good, I guess. Shader, GLSL, nothing. It's not good. Shader here. Are these mine? Yeah, it's installed. My bad. Templates. Okay, C#. We don't want C#. We want C++. What are Visual Studio extensions? What are these? C templates. C and C++, Windows Forms. Other, what do we have in other? Tools, build. Coding. No one codes GLSL, I guess. Never mind, I'm just going to do it without extension probably. Yeah, I mean, just okay. Show compact view. I mean, extension for vertex shader. Dot vert and dot frag. What do we name it? Pizza shader. What's happening here? No. Alright. Okay. As you can see, GLSL looks similar to C. Each shader begins with a declaration of its version. Since OpenGL 3.3 and higher, the version numbers of GLSL match the version of OpenGL. GLSL version 420 corresponds to OpenGL version 4.2, for example. Never mind. He also explicitly mentioned we are using corpora field functionality. So I need to write hashtag version 460 core. Save it. And as you can see, GLSL looks similar to C. Each shader begins with a declaration of its version. Oh, I just read that, sorry, what? Next, we declare all the input vertex attributes in the vertex shader with the in keyword. Right now we only care about position data, so we only need a single vertex attribute. GLSL has a vector data type that contains 1 to 4 floats. This one, based on its postfix digit. A vec4, vec3. Since each vertex has a 3D coordinate, we can create a vector input variable with the name apos. We also specifically set the location of the input variable via layout location equals 0, and you'll later see that why we're going to need that location. Let's see what happens here. Layout location equals 0 in vec3 pos. I'm just going to type pos void main. Why do we have more void? I don't know. GL position equals vec4 pos x pos y pos z. Save it. It does another thing. Okay, whatever. In graphics programming, we use a mathematical concept of a vector quite often since it neatly represents positions. Directions in any space and has useful mathematical properties. A vector in GLSL has a maximum size of 4 and each of its values can be retrieved via a vec.x, vec.y, vec.z, and vec.w, respectively, where each of them represents the coordinates in space. Note that vec.w component is not used as a position in space because we are not dealing with 4D, but is used for something called perspective division. Okay. We'll discuss vectors in much greater depth in a later chapter. To set the output of a vertex shader, we have to assign the position data to the GL position variable, which is a vec far behind the scenes at the end of the main function. Whatever we set GL position to will be used as the output of the vertex shader. Since our input is a vector of size 3, we have to cast this to a vector of size 4. We can do this by inserting the vec3 values inside the construct of a vec4 and set its v component, w component, what is v, to 1.0f. Okay, later chapter. We don't need to transform anything here because we have written all the vertices in the visible region. How do we compile the shaders? But I didn't write it like this. I need examples. I don't want to read all of it. Just give me a simple example, bro. I don't know, man. I think I'm just going to write it as string. For now. It probably explains later how to do it. So I'm going to do it like the guy says here. I'm just going to store it in a C string constant. Char array vertex shader pizza is called like this. New line. New line. Void main this shit. Sorry. Void main. New line. This game. New line. What is this? And this game. Version 460 core layout, new line, layout location equals 0 in vectory pos, new line, void main, new line, GL position, new line, then closing, okay. End of line, end of file, end of string. In order for OpenGL to use the shader, it has to dynamically compile it at runtime from its source code. First thing we need to do is create a shader object, again referenced by an ID. So we start the vertex shader as an unsigned in and create a shader with GL create shader. Where do you do it though? After opening in the loop. Here. You provide the type of shader you want to create as an argument to GL create shader. Since we're creating a vertex shader, we pass in GL vertex shader. Next, we attach the shader source code to the shader object and compile the shader. I see, like we created the vertex shader, but we didn't mention any shader source to it, so it doesn't know what it should compile. So we have to call the method GL shader source with our created vertex shader, and I don't know what, one shader, and like the source shader pizza, yes, and null. What that does, I don't know. Length. I know why we use null, but I'm just going with it. Yes. The GL. Where are we? The third parameter is the actual source code of the file action, and we can leave the first parameter auto null. We probably want to check if completion was successful after the call. Okay, we can check it. It completed. And if not, what errors are found, so you can fix those. Checking for compile time errors is accomplished as follows. Get shader IV. Okay. First we define an integer to indicate success and a storage container for the error messages, if any. This is info log. Then we check if compilation was successful with GL get shader IV. If compilation failed, we should retrieve the error message with GL get shader info log. So if it's not successful, yeah, it's fine. Do we need to do this? I don't think so. Fragment shaders. Yes, we're going to paint the pixels. The fragment shader is the second and final shader we're going to create for rendering a triangle. The fragment shader is all about calculating color output of your pixels. To keep things simple, the fragment shader will always output an orange-ish color, no matter what. That's weird. Yes, we can generate over 60 million different colors because of this. No? Yes, because of this. The fragment shader only requires one output variable, and that is a vector. Okay. Size that defines the final color of output that we should calculate ourselves. We can declare input output values with the out keyword that we here promptly name track color. Next, we simply assign a vector var to the color output as an orange color with an alpha value of 1.0. It is opaque. The process for compiling a fragment shader is similar to the vertex shader, although this time we use the GL fragment shader constant as this. That was so scary. The ad was so scary. Never mind. Yes. What's going on? I hope we are able to draw it, by the way. I'm going to get myself a coffee after the fragment shader chapter. The process for compiling a fragment. Okay, GL fragment shader. We need a fragment shader here. Where is the color? I want to use this one. I don't care. Yes. We didn't use GL compiler shader. Hello, I'm doing well. Thanks a lot. Thanks a lot. How are you feeling? What am I doing here? Vertex shader. Yes, I am okay. Why did you ask? Okay, I'm happy it's cool. Yes, what are we doing here? I could do it, yes. Right now? I mean, we could do it. So then I'm just ending this part here, and I will continue after I come from my break, guys. And we're going to keep working with the shader program. You just want to compile it once more though. It succeeded. Okay, I'm just going to say bye bye to you guys for an hour, and I'm going to keep the work up after I take a break. So see you later.